It works on my machine. If you've ever heard those words, or worse, said them yourself, then you already know why Docker exists. Docker is the tool that finally killed the works on my machine problem. And in the next 10 minutes, I'll show you exactly how it works, from the ground up. Let's start with the problem. Imagine you're building a web application. It uses Python 3.11, a specific version of PostgreSQL, Redis for caching, and a handful of system libraries. On your laptop, everything runs perfectly. But then you hand it off to a teammate, and things break. Different Python version. Missing library. Wrong config. Now multiply that by a team of 20 developers, a staging server, and production. Every environment is slightly different, and those tiny differences cause real bugs. This is called environment drift, and it's been one of the biggest headaches in software engineering for decades. What we really need is a way to package our application together with its entire environment, every dependency, every config file, every system library, into a single portable unit. And that's exactly what Docker gives us. So what is Docker? Docker is a platform that lets you package your application and all its dependencies into a standardized unit called a container. Think of a container like a shipping container in the real world. Before shipping containers were invented, loading cargo onto ships was chaos. Every item was a different size and shape. But as shipping container standardizes everything, it doesn't matter what's inside. The container fits on any ship, any truck, any crane. Docker containers work the same way for software. Your app, its runtime, its libraries, its config, everything goes inside the container. And that container runs the same way everywhere. On your laptop, on your colleague's machine, on a cloud server. Identical behavior, every single time. Now, you might be thinking, isn't this what virtual machines already do? Not quite. Let's compare them. A virtual machine runs a full copy of an operating system on top of a hypervisor. Each VM has its own kernel, its own system libraries, its own everything. That means a typical VM is several gigabytes in size and takes minutes to boot. A container, on the other hand, shares the host operating system's kernel. It only packages the application and its dependencies, not the entire OS. This makes containers incredibly lightweight. A container image might be just 50 to 200 megabytes. And it starts in seconds, sometimes milliseconds. You can run dozens of containers on a single machine that could only handle a few VMs. But here's the key insight: containers still provide isolation. Each container has its own file system, its own network interface, its own process space. Your application thinks it's running on its own machine, but it's actually sharing the kernel with other containers. This is possible because of Linux kernel features called namespaces and groups, which provide isolation and resource limits. Let's look at how Docker is actually structured. Docker uses a client-server architecture with three main components. First, the Docker client. This is what you interact with when you type commands like docker run or docker build. It's just a command line tool that sends your requests to the Docker daemon. Second, the Docker daemon, also called Dockered. This is the engine that does all the heavy lifting. It manages images, containers, networks, and storage volumes. The daemon listens for API requests from the client and executes them. Third, Docker registries. These are like app stores for container images. Docker Hub is the most popular public registry, with millions of pre-built images, everything from Ubuntu and Python to Nginx and PostgreSQL. When you run docker pull Nginx, the client tells the daemon to download the Nginx image from Docker Hub. When you run docker build, the daemon builds a new image locally. And when you run docker push, it uploads your image to a registry so others can use it. The client and daemon can run on the same machine, or the client can connect to a remote daemon. Now let's understand Docker images, because they're fundamental to how Docker works. An image is a read-only template that contains everything needed to run your application. But here's what makes images clever: they're built in layers. Each layer represents a change to the file system. The base layer might be a minimal Linux distribution like Alpine. The next layer installs Python. The layer after that copies your application code. And the final layer sets the startup command. These layers stack on top of each other to form the complete image. And here's the magic: layers are shared and cached. If 10 different images all use the same Alpine base layer, Docker stores that layer only once on disk. When you rebuild an image, Docker reuses any layers that haven't changed. This means builds are fast and images are storage efficient. When you start a container from an image, Docker adds a thin writable layer on top. This is where any changes your running application makes are stored: new files, modified configs, log output. The original image layers remain untouched, which means you can spin up hundreds of containers from the same image without duplicating any data. So how do you create a Docker image? You write a Dockerfile. A Dockerfile is a simple text file with a series of instructions that tell Docker how to build your image, step by step. Let's walk through a real example. The from instruction sets the base image. Here we're starting with Python 3.11 on Alpine Linux, which gives us a tiny 50 megabyte foundation. Workdir sets the working directory inside the container, like doing a cd command. Copy takes files from your local machine and adds them to the image. Here we copy our requirements file first, then install the Python dependencies with run. Notice we copy requirements.txt separately before copying the rest of the code. This is a Docker best practice. It takes advantage of layer caching. If your dependencies haven't changed, Docker skips the pip install step entirely on subsequent builds. Then we copy the rest of our application code, expose the port our app listens on, and finally cmd specifies the default command to run when a container starts from this image. Each instruction creates a new layer. Docker caches each layer, so only the layers that change need to be rebuilt. Containers don't exist in isolation, they need to communicate. Docker provides several networking modes to handle this. The default is bridge networking. When you start a container, Docker attaches it to a virtual bridge network. Containers on the same bridge network can talk to each other using their container names as host names. To reach a container from the outside world, you publish ports, mapping a port on your host machine to a port inside the container. For example, -P8080:80 maps your host's port 8080 to the container's port 80. Host networking removes the network isolation entirely. The container shares the host's network stack directly. This gives better performance but less isolation. And overlay networking spans multiple Docker hosts, which is essential for running containers across a cluster. Docker handles all the DNS resolution automatically. If you have a web container and a database container on the same network, the web container can simply connect to the hostname database. Docker resolves it to the right container's IP address. Remember how we said containers have a writable layer on top of the image? Well, that layer is ephemeral. When the container is removed, that data is gone. For stateful applications like databases, that's a problem. Docker volumes solve this. A volume is a directory that lives outside the container's file system, managed by Docker. Volumes persist even when the container is deleted. You can mount a volume into one or more containers simultaneously. Docker supports 3 types of mounts. Volume mounts are the recommended approach. Docker manages the storage location entirely. Bind mounts map a specific directory on your host machine into the container, great for development, where you want code changes to appear instantly. And TMPFS mounts store data in memory only, useful for sensitive information that should never be written to disk. Real applications rarely run as a single container. A typical web app might need a web server, an API backend, a database, a cache, and a message queue. Managing all of these individually with Docker run commands would be painful. This is where Docker Compose comes in. Docker Compose lets you define your entire application stack in a single YAML file. In this file, you declare each service, its image, ports, environment variables, volumes, and how it connects to other services. With one command, Docker Compose up, Docker creates all the containers, sets up networking between them, and starts everything in the right order. Let's look at an example. Here we define 3 services: a web application built from our Dockerfile, a PostgreSQL database using the official image, and a Redis cache. The web service depends on both the database and the cache. Docker Compose creates a dedicated network so all three services can communicate using their service names. And Docker Compose down tiers everything down cleanly. This is incredibly powerful for development. Your entire application stack starts with a single command, and every developer on the team gets the exact same environment. Let's put it all together and see how Docker fits into a real development workflow. A developer writes code on their laptop and tests it inside a Docker container. When they're satisfied, they build an image and push it to a registry. The CI/CD pipeline pulls that image, runs automated tests inside containers, and if everything passes, pushes the image to a production registry. In production, an orchestrator like Kubernetes pulls the image and runs it across a cluster of machines. Because the same image is used at every stage, you get consistency from development to production. No more "it works on my machine" surprises. Docker has also made microservices architecture practical. Instead of one monolithic application, you break your system into small, independent services. Each service runs in its own container, can be deployed independently, scaled independently, and even written in different programming languages. Companies like Netflix, Spotify, and Google run thousands of containers in production. Docker didn't just solve the packaging problem, it changed how we build, ship, and run software. Let's recap what we've covered. Docker solves environment inconsistency by packaging apps into portable containers. Containers are lightweight because they share the host OS kernel, unlike virtual machines. Images are built in layers for efficiency and caching. Dockerfiles define how images are built. Docker Compose orchestrates multi-container applications. And Docker enables consistent workflows from development to production. If you want to go deeper, check out our upcoming videos on Kubernetes, Docker networking, and container security. If you found this helpful, hit that subscribe button. Thanks for watching.